Right. Good afternoon, everybody. So we are switching our gears a little bit, and now we are going to listen and talk about the physics of the electromagnetic. Either Rosie is going to tell us physics of the AC, experimental introduction.
All right, well, thank you very much. So hopefully you all had your after lunch coffee so you can pay attention. And this will be the first two parts that I give. So, I think we can get started. So let's see. But before I do that, I just want to mention, since all of you are young people here, we're having the combined EIC users group epic collaboration meeting at Lehigh at the end of July. And there's actually a bunch of funding for early career scientists. So that'll cover a large fraction of your lodging and registration fees. So this is posted up here on the Indigo here, but it has the link. So I really would like to see some of you there as well. Just as a quick, all right, I have to push the right button. So Lehigh, for most of you who probably don't know, we're actually not far from here. Let's see, can I get this to work? Sort of. So we're over here right now. You guys are over here. So we're not very far. We can take the same airports. Most of you made it here. If you can make it here, you can make it there. Probably here, the entire conference is going to be walkable. So this is just my brief map of the event venue. The apartments where we're having young scientists stay, where the social dinner is, and my absolute favorite coffee shop. So this is just our venue. Looks like a physics room anywhere else. For those of you who stay, at least for the EIC users group, and I know a lot of you are theorists, but the EIC users group has a large theory component. We also have the social dinner that's will be partially funded as well by the grants funding, and that you can come in and see. And this is where it's at. It's at a nice restaurant on top of a large building at the high. So if you have any questions about this, feel free to ask me as well. All right, with that being said, we can go into lectures. So the first part of this, I'm going to talk about mainly the interaction of particles with matter, the detector requirements of the EIC, start going through the design of the epic detector. And for today, I'll talk about tracking detectors. So there's a lot of different subsystems, but mainly in order to divide this in sort of a reasonable way, I'll do that. And then I have here on the second lecture some of the other things I'll talk about. All right, so just a reminder, you've heard already. So one of the things is we're trying to study nuclear physics, and this is really the quest to understand the origin, evolution, and structure of the matter of the universe. So there's all these things that we don't fully know. How do the properties of the proton, like its mass and spin, come from this sea of quarks, gluons, and their underlying interactions? What is the configure and motion of quarks and gluons located within the nucleons? Now we've moved from just trying to think of this as a static thing, but they're moving around and fluctuating. What happens to the gluon density nucleons and nuclei at small x? For those of you who are new, I'll explain what that means. How well do these quarks and gluons interact with the nuclear medium? And how do these confined hadronic states emerge from quarks and gluons? So these are some of the things you've already heard about today. So just a few brief aspects. So I find the idea that we actually don't fully understand the spin, where the spin comes from the proton, or how its mass comes about, absolutely fascinating. Another aspect that is important is as you change the momentum of your probe, the structure of the proton will look different. So we have here the three valence quarks that we all learn about in kindergarten. But as you go down into X, you see that the structure of the proton becomes increasingly more complicated. And in fact, only 20 to 30% of the spin of the proton comes from the quarks. Another thing that's interesting, so we can measure the parton distribution function. So this is versus X. So this is just the fraction of momentum carried by the parton. And okay, the valence quarks, so the up and down, sensibly or peaked close to 1/3. But we have this gluon distribution that comes that it increases drastically as you go down in X. We see this. These are two different Q-squared plots, and I'll talk more about this kinematic variables, though you've had them this morning. And so we know that this can't go up to infinity. We know it has to saturate somehow. So these are things we don't know. Another thing is what do these distributions look like for protons that are in a nucleus? So all of these measurements are largely coming from bare protons. And that's great, but we know that the protons that are in nuclei are interacting via QCD with the other nucleons. And so how does this, does this look different for a proton that's in a nucleus? I don't think we fully know. And another thing that will be important is being able to do 3D imaging. So not just one-dimensional distributions. And this is because Rick is the only polarized hadron collider in the world. And so this ability to polarize hadron beams is going to be moved and well, not moved, it's going to stay there, but it's going to allow us to do EIC measurements with polarized hadrons and polarized electrons. So this allows us to do 3D imaging in space and momentum. We can look at the longitudinal structure, the transverse position information, the transverse momentum information. So these are GPDs, your TMDs that you've already heard some about. And quantum chromodynamics, of course, is you have this interesting aspect of QCD that gluons can interact with themselves, and just understanding better how this works in terms of the aforementioned distributions. All right, so how do we do this? And of course, it's an experimental talk, so I'll talk to you more about the experiments. So our big golden channel is deep inelastic scattering. So this is really where we collide the electron with, say, a proton, and we measure the scattered electron that's come out and whatever else. So this is really the golden process by which we will understand these different physics observables. And so there's a few things that we need to know. So one is we have some dials. So one is Q squared, so that's the resolution power. So it's the virtuality of the photon. We have the center of mass energy, the fraction of the nucleon's momentum carried by the struck quark, and our inelasticity. And so because at the EIC, which has Rick's versatility, we'll be able to collide at a variety of different center of mass energies. This allows us to then explore different X and Q squared and to better understand this. So you can see as we go up in, as we go down in X, you can get the same idea of the much more simple looking proton becoming something that's much more complex. All right, and just to center this, since we'll be talking about tracking and calorimetry, so we could draw a sort of a play, Feynman diagram's not really there, of what deep inelastic scattering can look like in the general sense, where your electron comes in with some energy, it gets deflected by interacting with your proton or whatever other nucleon you'd like. And this comes off with some change energy at an angle. Something happens over here. We'll talk a little bit about what that something is. And as you saw, we can determine Q squared precisely, but from the kinematics of this electron. So this is something we'll return to when we talk about electron identification and calorimetry and how this is important. And then the other thing we want to know is X, which we can determine from the momentum of the electron and from the Q squared. And so the idea here is that if you change Q squared, you're changing really the resolution scale. So you can measure something at large or smaller scales, depending on what your Q squared is. And if you change X, you're looking at different configurations. So this is where you can study the valence quarks versus the C quarks and gluons versus this area that we're really interested in, where the gluons will dominate. And so these processes allow us to answer different overarching physics questions. And so this is starting to be where it's important in terms of the experimental. So in this case, if we can measure everything that comes out in terms of neutral current, we can talk about parton distributions. So we can look at charge current inclusive DIS. So this is where, of course, the electron goes to a neutrino via W. And we want to measure all of the stuff that comes out here. This tells us about the spin flavor and structure of nucleons and nuclei and tomography via the transverse momentum distributions. We can also look at semi-inclusive DIS. So this is where we have a specific hadron and we measure then that with the remnants of our proton. And this gives us also, again, very similar to charge current, gives us the spin, flavor, structure of nucleon and nuclei and tomography. And last, of course, is exclusive DIS, where we really just measure everything and we have we find the struck proton on the other side. And this tells us about QCD at extreme proton densities, saturation, and we can do tomography and spatial imaging. So we really do. So one thing that you can see here is we really do want to know where this electron has gone, and we want the ability to measure everything that comes out of this out of the collision. So just I know you guys have a dedicated accelerator talk later, so I'm not going to go into too much detail here. Just the EIC machine parameters. So just down the road, there are two potential locations for experiments. So this is IP6, where the STAR collaboration is sitting right now, and IP8, where the S-Phoenix collaboration is. And then what we learn from this range of center of mass energy and the range in luminosity is there are different aspects of the physics that we can learn by changing the center of mass energy, which changes our access to X and Q squared, but also in changing the luminosity. The more luminosity you have, the more differential you can be in your measurements. So high luminosity is important. And for a lot of these measurements, another key aspect is the polarization, which is close to 70% for both the electron and ion species. We could even look at everything from protons up to uranium. So every nucleon is different. So uranium looks sort of like a hot dog, gold is round. There's all these other things that we can actually learn from these different process. And so, all right, this is the basic details. I'm going to focus on EPIC as our experiment. So this is the project detector, which is going to go into IP6. So that's going to be my case study. Since I only have 2 hours with you talking about detector 2 and everything else, I think would be too much. All right, so it starts, at least in my opinion, the journey, at least for me, starts with the EIC yellow report. Of course, we talked about the EIC and the long range plans for well over a decade prior to this yellow report. But what the yellow report really was an enormous community exercise to quantify the physics and detector requirements to be able to pursue EIC physics. So one thing is, an experimentalist, you're always like, well, how much is this going to cost? And is it worth the cost of the physics I'm trying to get? And so what we had to know going into this, before we even built anything, before we have any detectors, was what would we need to have in order to make something, make fundamental statements, make discovery science. And so this is dictated in this yellow report. Here's the archive link if anyone wants to go through it. There's actually quite a lot of stuff there that's really interesting and useful. But once we quantify that, we can then have guidelines for designing our detector subsystems. So one thing with detector subsystems, you want to make them as good as you can. But then the question is, how good is good enough? Because you could always throw more money and more time and more effort at something. At some point, you want to be able to say, okay, this is good enough. We're going to like move on to other things. And it's also important in terms of making decisions about like what technology to include or not to include, and all of these other things that I'll probably talk more about tomorrow. So this is sort of our timeline. So how does this work? I mean, for me, it was a little bit fascinating. I started graduate school after the LHC turned on. So this was the first time I got to see any of this process come through. So we had some long range plans for nuclear physics where we discussed the importance to the community of nuclear physicists of developing the EIC. Then we had this yellow report that I've already mentioned. And at this time, right after the yellow report, there was a call for joint proposals to submit proposals for the detectors. There was 3, Athena, Core, and ECHI. And in March 2022, so what are we in 2024? So 2 years ago, the ECHI proposal was chosen for the basis of the detector. And then from here, we kind of formed joint leadership with Athena and had our team in place starting in February 2023. And right now, what we're working on is the technical design report. So this is the big, along with the EIC collider itself, the big 1,000-page document, essentially, we have to give to BNL, assuring them that we can do everything that we said we need to. But the main important takeaway here is that the detector and machine design parameters are really driven by the physics objectives. So we're not just building things because they're cool, even though they are, but it is really to achieve specific requirements. And then again, before we move to the next slide, then when AIC was of course mentioned in 2023 as one of the important physics objectives and the most important for new facility construction in terms of nuclear physics. Okay, and then just as a flash, the EPIC collaboration. This was from our meeting at JLab, so last year, I want to say. And so we have a lot of international participation. So those of you who are experimentalists or, maybe experiment adjacent, come join us. You'll have lots of friends. Okay, so now let's get into the nitty-gritty details. What I'm showing you here is the extent of the EPIC detector. So the z-axis, I'm using the same z being the beam axis parameters. And then here is the x-axis, so you can see in meters how far the detector will extend. And so the total length of this detector is 75 meters. So that's even longer than the ATLAS experiment, which I think is one of the largest, I think it's the largest volume experiment right now. So, and part of this is to be able to measure everything that comes out of the detector, out of the collision. So we want to be able to get to these measurements I showed earlier where that requires us to measure all the fragments. Today I'm mostly going to concentrate on the center detector, which is about 10 meters long. So this is kind of in this green region. But the far backward electron detector and the hadron spectrometer are both quite long and extend quite some distance in either direction. And I will discuss this a little bit tomorrow. So just to spin back to what you already know, we want to look at things versus x and q squared. So we can take this detector and we can say, all right, well, what are we actually going to measure? So here we have the hadron beam going to the right and the electron beam going to the left. And where you measure the electron, depending on which detector, depending on the q squared of the particular collision, your scattered electron will go in some angle around here, indicated by this blue line. Depending on the x, so this is the struck parton momentum, you see that you get something going from low x where it ends up in the lepton end cap, all the way out here to the large x where you're measuring it in the hadron end cap. And so this is versus eta, which I repeat the equation, though I'm sure we're all familiar with this. And so this does mean that to dial x and q squared really is an exercise of dialing where you're measuring your particles in the space of the detector itself. All right, so basically this kind of comes back to the fake Feynman diagram I showed earlier, where what we really want to do is we want to dial q squared and we want to dial x because this tells us different things. And the way we do that is based on grouping collisions, depending on where the electron has gone and where the hadrons have gone from the collision. And so this allows us to change the resolution scale. What basically nature gives us a variety of resolution scales, we can look at them, and it allows us to change x, so we can look at these different configurations. All right, so let's start with the barrel. So I have here just a big, this is basically a block diagram of what the barrel will mostly look like. These auxiliary detectors to tag particles with very small angles are important. We'll mention them briefly, but that's what all of these little things that you probably can't read from here indicate. And you can see here that the asymmetry in the collision species, so hadrons versus electrons, does result in an asymmetry in the detector. So it can't be a symmetric detector based on this. All right, so maybe here I've talked at you a lot. Let's have a class exercise. Let's see if we know what particles are being measured where. So here I have, this is a hadronic calorimeter. This is an electromagnetic calorimeter in the center here, and we have tracking here and a muon telescope. So maybe let's start. Does anyone know what particle A must be? This dotted line indicates it leaves no track in the tracking detector. So photon, yeah, so this is a photon, no track and a shower in the calorimeter. What about B? So B has to be an electron, or it could be a positron, but yeah, we'll put one of these two. Now we have C. I heard a neutron, so we have then we can move on to D. Yeah, so it's be a pi on our proton. Then E here. Yep, so the E is the neutrinos, so you're basically out of luck with measuring those. And then last, probably easiest is F here, which is the muon. Which you don't have, depending on whether one has a muon detector or not. And so basically, depending on the species of particle you're measuring, you use different detectors combined together in order to be able to measure this. And so this does mean that you don't want to have just one detector technology. Okay. And so basically, almost all modern nuclear physics and HEP detectors have this very similar style. You want to put your tracking towards the center, followed by calorimetry, and muon chambers and that sort of things outside. And then this allows you to determine like the kinematics of the particles, their charge, their momentum, and ideally their identification. All right, so we can talk about some physics that's sort of our freshman or sophomore physics. When you have heavy particles, so this is anything but an electron essentially, moving through low density matter, they interact with the atomic electrons. So essentially, you now have to worry about the kinetic energy loss by a heavy particle incident on a light particle. So you have this equation for the energy loss. So for instance, if you have a 5 MeV alpha particles, so alpha particles essentially 4 nuclei, then you get a change in kinetic energy of 2.6 keV. So what happens is that a particle, as it's going through matter, it actually undergoes thousands of collisions before it loses all of its energy. So it's not that a particle coming out of the collision just interacts once with your detector subsystem and that's it. There are many of these interactions. And every time one of these collisions happens, and this will become important when talking about tracking, it loses a little bit of energy. But this doesn't have to always be in a straight line. So this actually will cause, it's not a lot, but the causing different deflections as the particle goes through the matter of your detectors. Now, the Coulomb force has an infinite range. So really the particle is actually interacting simultaneously with many electrons. So you see this sort of continuous energy loss as it goes through. And so then the energy required to ionize atoms is actually only a few tens of eV. So these collisions will actually liberate atomic electrons. The heavier particles that are coming out of your collision are now liberating electrons of the, ooh, that's exciting, of the material that came here. Oh, it's back. Okay, good. I was afraid that I would have to just pantomime this the whole time, which I would need more coffee for that. Huh? The second one, that's true. That's far away. I'm old and blind. All right. So the description for the energy loss of a charged particle was first done by Hans Bethe in 1930. So we have here this equation. And you can see that's mainly related to the velocity of the particle, the new electron density, and this is the electron density in the material, and the ionization energy. And one thing that you can see from this plot here is different materials will give you a different distribution. Even more importantly is different particles actually, like, so if these show the different momentum regions, they're kind of moving the scale around. But actually you can, different particles will have different ionization energy losses. So you can actually use this somewhat for PID. So the energy loss really depends quadratically on V and Z, but not on its mass. So we can see here we have the low energy distribution here. For low, so the energy loss decreases as 1 over V squared. And then there's this minimum that's usually at about 3 times the mass for most particles. And so you can actually determine what DEDX is versus the density of the material. Additionally, one area in the kinematics that we care a lot about is the relativistic rise. So that's this area over here. And basically the relativistic deformation of the Coulomb fields just essentially changes the physics distribution here. So you treat this somewhat semi-classically. All right, so in addition to heavy particles, electrons and positrons, they also will collide with the atomic electrons. Now for these guys, since they're basically the same mass as the atomic electrons, this is not a heavy on light distribution. So they lose energy faster and they'll scatter at larger angles. Some added complication to measuring electrons. And of course, we really want to find that scattered electron, so this is very important. Another thing is due to the light mass of the electron, they'll also lose energy versus bremsstrahlung. So basically, we know that accelerated charges will lose energy. They're in a magnetic field, so they'll lose energy due to that. So this is something to be taken into account. So energy loss, we have the same equation here due to collisions, but we also have to consider the bremsstrahlung loss. And we can look at what term dominates for electrons and positrons. It really depends on the incident energy. So which is the most important depends on what regime you're looking at. Now, there's one way in which we quantify the bremsstrahlung energy loss, and this is the radiation length here. So for different materials, you have this fairly complicated equation that involves the number of nuclei, the Z, and so on and so forth. But in the end, at least as an experimentalist, you don't really calculate this, but you do look it up in a table, and the PDG has everything listed. So for example, for lead, you have radiation length on the order of 5 millimeters. And this is really a very convenient quantity to characterize a medium where the bremsstrahlung dominates. So this is where high energy, above 10 MeV, pretty much where we want to do our physics anyhow, at least for that which comes out of the collision. So this is really how we will choose materials for our detectors. Along with electrons, we care about photons. There are, of course, 3 effects. So one is the photoelectric effect. So the photon that comes out can be absorbed by the atomic electron. And this is mostly important at low energy of the photon. So we're back to the few EVs, tens of EVs. This is easy to measure, hard to calculate. Then we have Compton scattering, where we're bouncing essentially the photon off of the electron. This really depends on the scattering angle. And last, and what matters at high energy, is also then the pair conversion. So in the presence of matter, the photon can convert to an E plus E minus pair. And we need this nucleus, but of course the mass of the nucleus is high, so it doesn't really matter in terms of the recoil. And this threshold's at 2 times the mass of the electron, of course. And so as no surprise, there is a mean free path before the pair production that's related to the radiation length in this simple equation. All right, so even though we'll mostly focus on tracking today, just a quick run, we have electromagnetic shower. So what happens is when you have a particle going through matter, it's interacting electromagnetically, you're going to have a shower essentially that occurs where, say, your electron comes in and it splits into a photon, another electron, they keep splitting, and things keep slitting down until you get to a shower that has a lot of different electromagnetic particles in it, and basically until it hits this critical energy where then they're just where the electrons and positrons then lose energy by ionization rather than this pair production. And so if you can measure all of the objects that shower off of your initial electron, you can know what its energy is. So the resolution of an electromagnetic calorimeter is usually in the order of 3 to 10%. Over the square root of E. And then here I'm using natural units. Since most of you are theorists, I'm sure you're very happy setting C and H bar and all those pesky things to 1. So we can all do that. And so yeah, so this is our radiation list. This will become important when we talk about calorimeters tomorrow. But in addition to electromagnetic showers, you also have to worry about hadronic showers. Hadronic showers now, or if you have a neutron or a proton that come in, they're a lot messier than the neat distribution you'll see in terms of electromagnetic showers. So this is why the H-cal are usually on the outside. You don't want to disturb your electromagnetic process. So another aspect that is quite important is that the nuclear interaction length, which should not be confused with the radiation length, is usually in general a lot longer than it is for the radiation length. So what does this mean? This means that a particle that is going to interact via QCD in the matter that it's moving forward will go a lot further before it has an interaction than it does if it's interacting electromagnetically. So this is why HCALs are huge and they're made out of steel. And EMCALs are usually much more compact. And now I a little bit wish I had brought some. I had traveled over to Brookhaven and stolen some of the pieces to show you guys. But next year I'll remember that. But another aspect of the hadronic shower is that it actually has an electromagnetic component. So pi zero. So basically, if we assume nature is even, it'll be just as likely to make a pi zero as a pi plus or a pi minus. But the pi zero instantly decays to 2 photons. So then you have an electromagnetic shower, and this actually behaves just as this shower here. So both of these aspects are important. And I have here just this chart for some commonly used materials, the difference between the radiation length and their nuclear interaction length. And the resolution of hadronic calorimeters tends to be a lot worse than it is for electromagnetic calorimeters due to this. All right, let's talk about tracking. Maybe I'll pause and see if there are questions before I launch into new technologies here. I know it's after lunch, so. And this room is very warm, actually. So, but.
They switched on from heating to cooling like 1 week ago, but the building is very old. So before it switches physically, it takes some time. I was told that it was worse last week.
Oh, okay. Okay.
By the end of the school.
Yeah.
That's why I have this. Okay.
Yeah, no, this is very, very common in physics building. They do the same thing in my institution. There's definitely been times where I've had the windows open because I can't turn off the heat. Okay. But hopefully you guys can stay awake, because now we're gonna get to the main meat of what I want to talk about in this first lecture, which is tracking. And so all tracking technologies really are based on the idea that charged particle leaves a trail of ionized atoms and liberated electrons when traveling through matter. So we can see this here where we have some charged particle going through silicon and it's leaving some ionization. And what we can learn from this is we can actually measure and reconstruct the trajectory that the particle is taken by looking at where this ionization energy comes from. There really are 2 main technologies. So one is using gaseous tracking volumes. So this is basically where the liberated electrons that we see here drift towards sensing wires where the signal can be recorded based on the electric field. The other is using semiconductor technology with silicon pixels or strips. And so there's a few reasons we want to do this. So, you know, all of these detectors are placed in a large magnetic field. So you can see here we have curvature of the line as a particle goes through the material of your tracking detector, and each of these points represents a measurement. From knowing its curvature, you can actually, and knowing the magnetic field, you can actually determine its momentum, which is a key aspect. Another part of this is that's important that I won't be able to go into too much today is we also are interested in looking at secondary vertices versus primary vertices. So particles that decay via the weak force will go some distance before they decay. And this is useful for measuring, say, heavy flavor, and these like heavy flavor jets and other aspects. So, but there's a few issues. So one is this multiple scattering. So you can see here that the path of the particle is not as neat and clean. See if I can actually go backwards, as I've shown here, where it comes to the tracking detector and looks okay. It really does wiggle about. So you really want as many points as you can put in. Now the issue is that if you put more and more material to make more measurements, you're actually putting more material that your particle is going to interact with. So this is not exactly a zero-sum game where you can just make it as dense with as dense as you want. Now, but one thing we do know is since it can be pushed, say, in this case, it could be pushed up and it could be pushed down, and we expect given the nature of the universe, that it should be pushed in one direction as often as another, that you should get some Gaussian distribution with some tails in terms of where the particle finally has come out in your tracking detector and where it has come in. But we really do want all of this for a good tracking detector. We want it to be high precision, we want to have a good large signal, and we want the tracking detector to be as low mass as possible to not disturb our particle. We also need to know the resolution. So there's a lot of factors that play a role in terms of your resolution. So of course, one is the number of and spacing of your tracking points. So usually we try to have our track points kind of evenly spaced. We were physicists, we like things to make a nice little pattern, having these like different lengths would be strange. Also, you can do things like square root of n, which makes life a little bit easier. The more points you have, the better your resolution. So generally, we take our resolution here. So this is our width of our distribution, and it's based on momentum. And this is because something that goes really high momentum will go kind of straight through your detector. Of course, it doesn't bend so much so you can tell what its momentum is. But we divide it in terms of the general term and then the transverse momentum of the momentum, and then this multiple scattering term. So ideally, the easiest way, we would want to have a large path length. So if we come back to our drawing here, the more of these points, the better it is. But then the bigger your detector is, the more mass you put in and so on. So we want good length. We actually want to have a large magnetic field. This allows you to measure higher momentum particles based on the bending ratio. But the problem is that the magnetic field is too high, your lowest momentum particles will curl around in the field. So what I didn't show here, but you can all imagine, is that if you have something that's really low momentum, it might come out and come around and just do a little circle here and never come out of your tracking volume. So these are things to take into consideration. So at some level, you really can't measure all things to the same precision. Okay, so I think we can talk. So that's a general idea of tracking. So coming out of the yellow report. So now we're going to specifically talk about EPIC. So if you go to the beginning of the yellow report, we have these detector requirements. So don't worry about the acronyms so much because I am going to go through each of them. So I know us experimentalists like to use our 3 and 4 letter acronyms all the time. But we had a couple of different requirements. So one was for the vertex detectors, we needed to be able to identify primary and secondary vertices. So this vertex detector has to be your sort of innermost detector in order to be able to tell where the collision has happened and what has come from the primary collision. So this is the initial interaction of the electron with their ion versus decay products. We really want it to be low material budget and have this high spatial resolution. So then the center and end cap tracker, so we were talking about this, we're talking about the trackers that are on the, not right in the center here, so this little cylinder, but the trackers on the outside. We want them to have high precision, but low mass. And so this is largely using maps. So we have tracking layers in combination with pixels and with gas detectors. So this was what came out of the requirements. And so there's a couple of different things. So our challenges are we want efficient pattern recognition. So taking data at a fairly fast rate, we have to separate our signal from our background. And so this is what they mean by pattern recognition. We want to know, where the vertex is essentially. And so one strategy was we wanted to have redundancy on the measured space point coordinates. So what this means is we don't want just one subsystem measuring it. You want more than one subsystem, and you want them to be able to agree with one another. So we also needed very low material budget for the central tracking region. And this is really important for momentum resolution. So I'll talk about these in a slide or so. But we then made this choice on monolithic active pixel silicon. So this is when you hear people talking about maps. This is really what it is. This is a technology that's been used now in a number of experiments. I think it started in STAR, but Probably I might not be completely correct, so somebody might throw something at me. But I know that a lot of what we're using right now is being developed in Elise, and it's also being used currently in Phoenix, which is just down the road. Some other things that we had to worry about is we had to deal with this solenoidal magnetic field. Now, inside the barrel, the magnetic field is fine. But in these end caps, and I'll back up a step, in the end caps, the field is less. So the magnet here is in purple. And so when you're in the end cap region, you have a lot less magnetic field. This means a lot less bending. So you had to deal with that in terms of your design consideration. And the magnet is what the magnet is. So you can't really be like, oh, can we just, I don't know, put an additional magnet in there? It doesn't quite work like that. We also had this limited lever arm. So our solenoid and overall detector design constrained the size of the barrel. So our solenoid had to be a specific size. One of the design parameters was that the detector had to fit inside the babar magnet. Actually, who here knows what babar was? All right, so
I heard this.
You've heard of it. Yeah, so it was an experiment. So maybe let's take one little step back. The babar experiment, which ran in California, had so making a magnet, like one of these superconducting magnets, the large magnets that are used like for Atlas or CMS or for STAR. STAR is a little different, but for Phoenix, it is actually very hard and very expensive. And so we originally designed, so the babar experiment ran, and then they gave their magnet to Phoenix. So this magnet had been running for 20 years, so shipped across the country in a big boat over in Phoenix where it's running right now. Then the idea was to design everything to fit within the babar magnet. Now, the issue is that, okay, well, it's kind of going to be a 40-year-old magnet by that point. You know, I mean, from my perspective, 40 isn't so bad, but, you know, for magnets, it's a little different than for people. And so then the decision was that we would actually design and build a new magnet, but it had to be the same size because there is actually a somewhat degree of risk in making a new magnet and having it not actually work. I'm not a magnet person, so I just have to take that on faith. But that did constrain our size because we have to be able to use the babar magnet of everything. All right. It's probably more about the politics than you wanted to know. But the other aspect that we had to worry about. And then so these aspects meant we had to have fine space resolution and granularity. So this is silicon sensors. And then we really tried to build in synergies amongst the different components. So not only do you have different detector technologies, but they interact with each other in a different fashion. So this is all based on your decision making. Another aspect that we really wanted to worry about is we do have a low interaction rate, which normally is really good. Hey, you know, 0.5 gigahertz is not so fast. You can easily measure it, but there's actually significant background due to synchrotron radiation and other things that I'll discuss tomorrow that you have to be able to disambiguate. And so we really just needed additional micro pattern gaseous detector layers, so we couldn't do this with maps. So here I show the central. So now maybe we'll back up a second. I'm now focusing in on this thing that's here in yellow. So we're zooming in a little bit. This is then the tracking technologies. In green, we have maps. So this is silicon chips, basically. And in blue, we have MPGADs. So this is gas, essentially. And then red is our PID detector that I'll discuss tomorrow. So the silicon vertex tracking, we have 5 layers. This is based on this precise technology that was developed by Elise. The MPGADs, so this was micro pattern gas detectors. These were detectors that were used to cover a large outer tracking volume. So this is something that plays a role in your decision making. Pixels are expensive, and if you want to, the further out from the interaction region you go, if you want to really cover, the more you'll really need. But these gas detectors tend to be better in that circumstance. You also need good timing, which they do well. Another aspect that was important was also being able to install them and bake out the beam pipes. So the silicon has an advantage there. And we'll talk a little bit more about PID tomorrow, but you also need resolution. So the ACL GAD works with particle identification by time of flight. So this is essentially, if you know the momentum of a particle and you know how long it took to get from point A to point B, you know its velocity, thus you know its mass. So just a brief, so this basically works as all tracking detectors. You have some ionization energy. So on the left here, this is the micromegas. So this is micromesh gaseous structure. The charged particle goes through and ionization, it ionizes the gas, which drifts then to this readout region, which is on the other side of this mesh. So then you have this amplification region in order to be able to get your signal. And so both, and then the other technology here is the micro Orwells. The difference here is that you have a resistive layer above your readout electronics, and you have a single stage amplification. So basically you have a well structure that replaces the separate mesh and amplification gap here that you have over here. But both these technologies are quite good. And one important aspect is the micromegas have now been demonstrated to work in a cylindrical geometry, which you can guess being able to build it in a cylinder is a necessary part of being able to use this technology. And so these are both of the gaseous detectors that are being used in tracking for EPIC. Maps. So this is monolithic active pixel sensor. So one advantage you have with a map is that the sensor and the readout electronics are integrated on a single piece of silicon. So this is where the monolith part of it comes from, just one piece. And each pixel in the maps detector is an active element. So you could think of each of these as like a pixel, like on a camera. And so you can have very small pixels, so they're on the order of micrometers. So that gives you this high spatial resolution. And because of that, you can also have a high density of these pixels, which gives you an excellent granularity. So these are one reasons why you would use this for your vertex detector. They're very thin sensors, which is important for our low material budget. They're radiation hard and they're very fast. So radiation, of course, you're putting these things in the center of the detector. They're going to get hit a lot. You want them to keep working. Just as and they always talk about this being a CMOS, which is just complementary metal oxide semiconductor. This is basically all semiconductor chips, but people like to throw these acronyms around. All right, so you build all your tracking, and then what do you do with it? So now you have different subsystems with different patterns, and we want to turn this into physics. And so, we have a couple different routines. So one is this Kalman filter. So what this allows us to do is to extrapolate from layer to layer where we think a particle is going to go, filter, then make the measurement of where it has gone, and then filter the distribution of the particle. So essentially, you work from the outside in usually, and this allows you to determine. Because when you have a bunch of particles now going through your tracking detector, you want to know what hit belongs to one particle and what hit belongs to another and where they've gone. And you have to do this in somewhat of an iterative routine. And so one nice thing that the nuclear physics and high energy community have come together with is we have ACTS, which is very originally named a bombing tracking software. But the idea is that this isn't unique to us. This isn't unique to EIC. Everybody from STAR to SPhoenix to Atlas and CMS and so you can tell I'm a root physicist and everybody in JLab also uses tracking. So this actually allows the community itself to solve these problems in a coherent way. And so then what you would want to learn is you would need to calculate basically these track parameters. So you have some local parameters which describe the sensor surface. So you have, each of these gray boxes sort of represents a pixel, for instance. So you need sort of a longitudinal and transverse there. Then you have the azimuthal angle and global coordinates, with respect to the z-axis and global coordinates, the momentum, and then the time of the hit. Now, this timing of the hits is actually very important due to the background. The collisions, of course, have a specific clock cycle in terms of when the bunch crossings happen in the center of the detector, but background has no timing, more or less. At least when you're talking about synchrotron radiation, that doesn't that's not directly correlated with the bunch crossing cycle. So you can take all this, and now we go back to where we started. We have to show based on Géant calculations of our various subsystems that we're meeting the requirements that we put forward. So what I'm showing you here is some preliminary tracking performance out of EPIC. So this was shown last week at this conference, if you want to go look up this particular talk. And this is looking at the momentum resolution and the transverse DCA. So this is the distance of closest approach. And so this is for backwards and forwards. So there's different ADA regions dividing the top versus the bottom. And you can see this is for pi minuses. So one will calculate this for a variety of different particles. But what the main takeaway here is that the requirements are met in the central region, and the requirements are actually substantially met in the forward hadron and backward electron regions. So this is just indicating that we mainly get in by these pink lines here. So great. This indicates that we made the right choices. Of course, I mean, we're many years into this process, so hopefully that would be the case. So I think this gives me kind of to the end of what I wanted to tell you today. But I think if you want to kind of summarize is, detectors, we use these basic properties of particles that you all learn about in, your kindergarten physics classes. And we combine them together to determine the kinematics and flavor of those particles. And this allows us to answer these fundamental questions that we're interested in. So modern collider detector really is a combination of a bunch of detector technologies that they're designed to work in concert in order to achieve a specific set of physics goals. Now I'll talk about calorimetry and PID tomorrow, but tracking really is at the heart of all modern nuclear and HEP experiments. So if you don't know the kinematics of your particles, you know nothing. So your tracking is very important. It's also it's also very difficult. It's a harder technology, and in some respects, calorimetry can be a little easier, and we'll talk about why that is tomorrow. And some of the other detectors are easier to use, but your tracking really, it needs to be fast, it needs to be small, it needs to work in a very high radiation environment, since you have to have it at the center of your detector. And so it's actually quite a challenge. So I'm actually not a tracking expert, but if you talk to people who are, they can say why their hair is white and how much trouble they've had in terms of doing this work. But so maybe I'll stop here and see if there are questions. And
what is the seed while tracking? I hear all about these seeds, like truth seeds and radioliptic seeds and all this stuff, but I have no idea what it means.
Yeah, so that's actually a great question. So when you're fitting a function, right? You can't just say, even if you know if it's Gaussian, if you just say, hey, fit this, and you don't start your fit somewhere, the fitting routine might return something that's absolute nonsense. So for the tracking fitting routines, there needs to be some easy, quick way of starting the fitting routine. So where are you starting? Now, right now, of course, because we're simulating everything, we know, and maybe we'll start with how does the simulation work? So we take some event generator, Pythia, whatever your favorite, poison is. And we also have our detectors modeled in Géant. So we take then the Pythia event, we run it through the Géant essentially, and simulates the reaction of the detectors. So now we say, okay, now we're going to run our tracking algorithm on the simulated Géant data. Now, because we threw the truth, we can say, oh, well, we know exactly where this went because we're God in this experiment. We could use that as our starting point. And that's a lot easier to do, and that's usually where we start from. Now, the issue, of course, is when we build the detector, we will no longer be able to do that because we can't know the truth. And so then the question is, what is the best algorithm you can use using a realistic seed? So this is something that you can actually measure as opposed to knowing where it was in terms of the truth.
So that's basically the starting point of the track.
It's the starting point of the tracking routine. Yeah. Other questions?
When you say that time and distance, I refer to drift time or drift distance. And also which one you first measure from the detectors like that. You first get the timing information and then get the drift distances.
So, yeah, so there's actually a couple different, there's different timescales. So when I'm talking about and I'm also short, so we'll stand right in front of the podium, but when you have the drift through, say, the gaseous detector, because I'm not talking about TPCs, those are large and that has different, the drift time there is the readout time. So this is how long it takes the detector, once it gets a signal, to actually like essentially read that signal out. So you want that to be as fast as possible. There's also the time it takes a particle to go from the collision interaction to that detector. That time, then, if you know that precisely, you can determine the particle species by determining the velocity. So those are two different time scales. And then, of course, the other timing is we know when the collision should happen in terms of the frequency. So we know when these bunches are crossing. And so then there's a clock cycle based on the accelerator, essentially. So now if you're talking about something like a time projection chamber, which is used in ELISE and SPHENIX and STAR, there the drift time is actually longer than the collision time. So what that means is they actually have signals from multiple collisions in the same readout, which is complicated because you really only want signals from one. For like the gaseous detectors, the MGADs that we're using for EPIC, those are fast enough that won't happen. However, we still have the background. Nobody gets away without having any background.
You say that backgrounds aren't a huge problem because they don't have that time dependence. Things like a synchrotron background are like easier to filter out because they tend to be kind of constant over the entire reaction. But are there lots of backgrounds that start with the collision that you have to try and filter out?
So you can. So the problem. What you can get is there's a couple different things that can cause background. So one is that our bunches have on the order of 10 to the 10 particles in them. We really want one collision between one ion and one electron at every time. You can have two. And it's just because the problem is we want the collision rate to be high enough that we kind of see a collision every bunch crossing, but that means then the probability is finite that you have 2 or 3. So that's one background, is how do you separate two different collisions that can happen. Other things that can happen is you can have downstream collisions, so beam gas events. Those tend to be a little bit correlated with the bunch crossing. And part of it is in the collider itself. So you have the ring. So if you have a particular ion and it fragments, it's no longer going to have the same charge to mass ratio. So they often get swept away. But if you have a collision that's very close to your detector, then those particles will then go through it. So you do have other somewhat more in time backgrounds. The synchrotron radiation, of course, has no time, but it is also large. And part of it, and what I'll be discussing tomorrow a little bit, is we're also doing streaming readout. So that means in any time frame when we take the data, we'll have all of these backgrounds to deal with.
Why does a hadronic shower have the two components, the electromagnetic and hadronic part?
Mainly because so essentially to first order, we could say everything that comes out of any nuclear interaction is a pion. I mean, this is largely true. And so it will kind of be somewhat even in terms of pi plus, pi minus, and pi zeros that come out. The pi plus and pi minus, they'll still only interact via QCD. So they're still do other, other sort of QCD based interactions, but the pi zero instantly decays into 2 photons. And so, and those photons, of course, will only interact electromagnetically. So basically, anytime, you're having the shower of pions that's forming, anytime a pi zero is formed, it immediately decays into an electromagnetic shower. And the other issue is that since the electromagnetic interaction, the radiation length is so much shorter, that basically immediately gets absorbed, into the detector. So you kind of have this energy that's leaving your shower with a statistical aspect. So in fact, I mean, hadronic calorimeters, they're essentially like steel and scintillator. And so they're not so different than the electromagnetic ones in that sense.
Let's see other questions, so let's thank Now I know that a few of you haven't yet taken your meal cards, so if you haven't gotten your meal card, let's go together and we can have it. So we have half an hour break.